Here are three more identities that we can use to simplify trigonometric expressions. We call these ones the Pythagorean identities because really they're based on the Pythagorean theorem, which we've talked about in class. So here they are down here. Notice all three of them involved taking our trigonometric functions and squaring them. So when you see squareds with your trig stuff, that's probably a good indication that we're going to be trying these Pythagorean identities. So let's go ahead and take a look at how these three will work. And again, you may want to have your formulas or your identities in front of you for simplifying some of these. So here's our first example. I've got sine squared of pi over 8 plus cosine squared of pi over 8. Well, it's very important that those angles match up. So if they aren't the same thing, we'd want to make them the same thing first. And looking back at my identities, I see that I have one about sine squared plus cosine squared. Sine squared plus cosine squared, as long as your angle is the same, is always equal to just 1. So this will simplify to just 1, no matter what those angles are, as long as they match up. Okay, my second one, I'm noticing my angles are not the same. However, I can use my periodic properties to make the angles the same thing. Recall that the period of the cosecant graph is 360 degrees, so I can subtract 360 from this angle, and I've got videos about periodic properties if you want to go back and watch one of those. And so 380 minus 360 leaves me with just 20 degrees. So now I do have the same angles right there. So what I want to look for is a property or an identity that involves cotangents. And so looking back in my notes, I can see that cotangent squared of an angle plus 1 is equal to the cosecant squared of that angle. And so I kind of have that property, although I'll have to do a little bit of rearranging to make this work. And so what I can try to do is maybe I'll subtract cosecant squared from both sides. And so I'd be left with cotangent squared of theta minus cosecant squared of theta, which is what my expression up above is saying, but then that 1 needs to be moved out of there, so I could also subtract 1, which means cotangent, I'm just rearranging terms here, so cotangent squared of theta minus cosecant squared of theta, whatever that angle happens to be, should be equal to -1. So this identity will, or this expression will simplify down to just -1 using that identity. Let's take a look at, if you think these are tough, let's take a look at a couple more that are even more involved in these last two examples. Okay, so I've got the sine squared of pi over 12 plus 1 over the secant squared of pi over 12. Well, both angles are the same, so that's good news, but I definitely don't have an identity that involves all this wackiness over here. So I think what I'll do is just kind of focus on this piece. And using some inverses, using some reciprocals, which we looked at a couple videos ago, I know that the reciprocal of secant is just cosine. And so maybe I'll rewrite this problem as sine squared of pi over 12 plus the cosine squared of pi over 12, since that is just the reciprocal of secant, and if this one's squared, then that just means cosine will be squared. And now I see that I do have one of my identities. Since I've got sine squared plus cosine squared, that identity said this is going to be equal to just 1. So even though it looks like an awful problem, it just simplifies down to 1. And then here's our very last example, definitely the most involved one we've seen. So first thing I'm going to do is I'm going to try to make all my angles the same. Using my even-odd properties, I know that a cosine is an even function, which means this negative sign in here doesn't really matter. The cosine of -15 is the same thing as the cosine of +15, so I'll just swap that out right away. Same is true for the reciprocal of cosine, which is secant. So secant of -15 would be the same thing as the secant of +15. So there's everything with the same angle now. They're all 15s. And maybe I'll start with this back piece, because we kind of did that on the last example. 1 over the secant squared is the same thing as just cosine squared, using some reciprocal identity properties. So this would be the same thing as the cosine squared of 15 degrees. Okay, so that part's not too terrible. Let's take a look at this first piece. Let's see. I'm going to start by rewriting tangent using my quotient identities. Recall from the last video that tangent of 15 is just the same thing as the sine of 15 degrees divided by the cosine of 15 degrees. Okay, and then let's see what happens. I'm going to leave the other two pieces the same. And we may not, you may not know to do that, but I know what's going to happen once we do this. So I'm going to choose to leave those the same. Part of these problems is just kind of figuring out ideas that that work and trying strategies if your idea doesn't work. So all three of those pieces were being multiplied together. Since I've got a cosine of 15 on the bottom, that'll cancel out with the cosine of 15 that I was multiplying by. So those two pieces are gone. What's left is sine of 15 times sine of 15. Well, when you multiply something by itself, that just squares it. So I get sine squared, or sine of 15 squared, I should say. That's just the notation we use. So all this first part just works out to be sine squared of 15. The second piece had me adding the cosine squared of 15, and as we've talked about, sine squared plus cosine squared is just equal to 1. Okay, so that's how these difficult Pythagorean theorem identities work, using them to simplify trigonometric expressions.